In this video, we will be looking at the relationship between circular motion and simple harmonic motion. So you've already dealt with simple harmonic motion in the previous course in Physics 9110. For those of you that would like to review the material, I've included links to Liz's videos as well as to some other online resources at the very bottom of this page. In this video, what we're interested in is the projection of circular motion on one of the axes of the coordinate system that we use to describe it. In particular, we're interested in how to describe the position, the velocity, and the acceleration of that projection as a function of time. So here we have our Earth undergoing uniform circular motion around our Sun at a radius r. In order to accurately describe this system, we need to have a way of describing the position of the Earth. So that means we need to define our coordinate system. Because this is a standard two-dimensional problem, I will define the standard two-dimensional axes. And once we've done that, we can define our angle theta, that is the direction of our Earth. We know that for such a system, the angular velocity or the angular speed of our Earth, of our object, is defined as omega equals theta divided by t radians per second. That is, our angular velocity in radians per second is the angle swept out by our object in a given time t. We also know that if we begin analysing our object when it is at a start position of theta equals 0, we can rearrange the above equation to give us our angular position. So theta equals omega times t, and this is an analogue equation to our distance equals our speed times time. And this is a useful equation, but it's not quite general enough because it does not account for the possibility that we may have to start analysing our system when our object is starting at some other point in its motion. So for example, if we are to analyse our entire solar system with its 8 planets, 9, then we will find that not all of those planets will start at theta equals 0. So we define a more general equation. We say that if we say our object will be starting at an arbitrary angle phi, then our angular position is given by omega t plus this offset angle. And this is the general equation for our angle theta in a circular motion system. So what we're interested in is the projection of this motion on the x-axis. So what we're looking at is essentially the x component of our position vector, of our r vector. If we start with our simple system, so with our Earth or our object beginning at theta equals 0, and we can plot our x projection, which is xr on the y-axis, as a function of the time, or the orbital time period. In this case, years. So we can see that in the initial state, because our Earth is located on the x-axis, the x projection is maximum. That is, the x component of our vector is at a maximum and is equal to r. As the Earth rotates around the Sun, we can see that x projection decreases until a point where it equals 0 and then becomes negative. Halfway around our orbit, we can see again that our position vector is directly along the x-axis but in the negative direction, so our x projection reaches its maximum negative value of r, and so on. And this behaviour is periodical, so we see that year after year we have a curve that looks something like this. And what we're interested in is how we describe that curve. So looking at it, it looks remarkably similar to the general form of a cosine curve. And when we have the general cosine curve, so we have on our x-axis the angle theta and our y-axis is the amplitude of our curve, we know that we can describe that by the maximum amplitude of the curve multiplied by cosine of the angle. In our case, we know that our maximum amplitude is equal to our radius r, and we're not looking at our projection in terms of theta, but in terms of t. So in order to describe our projection as a function of time, we need a way of converting our angle theta in terms of time, which we have. So if we substitute each of those values into the general equation for a cosine, we find that we describe our projection of our orbit using r times cos of omega t plus phi. From that equation, we know that to describe our velocity, we have to take the derivative. And that gives us that our velocity is equal to minus r omega sine of our omega t plus phi. And we do the same thing to find our acceleration. We differentiate our velocity, and that gives us that our acceleration is equal to minus r omega squared cos of omega t plus phi. If we look closely, or not even particularly closely, at those equations, we will see that they are the equations of simple harmonic motion. So the projection of the orbit of our object undergoing circular motion is described by simple harmonic motion. And that is useful for a number of reasons. So first of all, obtaining results for simple harmonic motion using a circular motion setup in the laboratory is a very simple experiment, and is exceedingly useful for understanding how to interpret simple harmonic motion results in detail. And that in itself is useful because simple harmonic motion occurs in a fairly large number of places in nature. So a detailed understanding of simple harmonic motion can give us a very detailed understanding of the world that we live in. So as an example, it will help us to understand the universe, or at least those parts of the universe that we can directly observe. So when astronomers are looking, for example, for extrasolar planets, or at the rotation of two black holes or binary star system, they don't get to choose the angle that they see the system at. And more often than not, we see a side-on view. That is, we see the projection of the orbit on one of the axes of the system. So in order to interpret the orbit and what's happening in that system, they need to be able to interpret simple harmonic motion. And the interpretation of that, in this case, can give us, for example, at a basic level, the size, the speed, and the orbital radius of, for example, extrasolar planets or the stars in a binary star system. So at its most basic level, understanding that circular motion can be interpreted or described by simple harmonic motion really does allow us a much greater understanding of the universe that we live in.